my immense pleasure to introduce Professor Higham. He is one of the very, very few people that really inspired me. So doesn't happen very often that you introduce one of the writers of your textbooks, one of the, I call them the gods of numerical linear algebra. So we have accuracy and stability. This is what I studied during my PhD. Then we have some MATLAB. No, this comes later. This comes then a MATLAB guide that I think everybody has seen. And then we have, this is a new trend because it opens up new fields, so matrix functions of matrices, matrix functions. And then every doctoral student has seen this, how to do some technical writing, and the list goes on and on. So, it really doesn't happen very often to say that the speaker today literally shaped and changed a field. I cannot name many other speakers that are as influential in my domain as Higham. So he won pretty much everything that you can win in our domain, starting from the Householder Award, which is the best dissertation in numerical linear algebra, then Leslie Fox Prize, and then fast forward ERC Advanced Grant, Academia Europea, and you name it. So I am super happy to have you here, Nick, and very happy to hear about multi-precision algorithms. Thank you for accepting the invitation. Okay. Oh, and maybe I should mention, Nick is also the president of SCIA.
Thank you for that very nice introduction, Paolo. The check will be in the post later. So I'm going to talk about multi-precision algorithms today. And just let me say what the philosophy of preparing these slides was. Because I know that people here from a variety of different backgrounds, some from maybe the math side, some more from the computational science, computational engineering side. So I'm aware of that. I'm not going to give lots of theorems and proofs and nitty-gritty detail. I think it's more useful to give the overall sort of high-level view and picture to illustrate what are some of the issues in numerical computation nowadays, and some of the ideas that I've been thinking about. And hopefully I think that will be more useful than just to go into low-level rounding error analysis at some great level of detail. I mean, certainly when I go to a talk, I'm hoping to get one or two ideas out of it that I can maybe apply to what I do. So hopefully that will apply to you today here. The slides are available on the web, which is from actually my home page and then /talks/lecture.pdf. So feel free to download those and follow along. There are a few links in the slides, which I'll show as we go along. And at the end of the slides, there are some further references where you can get more detail. So roughly speaking, I think there's about 2.5 to 3 hours worth of material here. I'm planning to take a couple of breaks. Not quite sure when, but at some point we'll take a couple of breaks. And I want to not go too fast. I'm going to go nice and slowly and encourage you to ask questions. I think it's better for me and for you if you chip in with questions at any point at all. So feel free to just ask a question at any stage whatsoever. So that's I guess the basic initial comments. And here's an outline. So multi-precision arithmetic is the underlying technology here. So we're talking about floating point arithmetic, not just single and double precision, which we've had pretty much since the first computer, but we now have half precision in hardware on high-end GPUs, and that's becoming more and more widely available. We've got quadruple precision in software. We've actually had that for quite a while in the form of compilers. Certain compilers have supported quad. But it's becoming more widely available in other forms of software. And the drivers like high-performance computing, moving towards exascale, energy, minimizing energy usage, I think are forcing people more and more to think about what's the appropriate choice of precision and not just running things in double by default. And one theme here is using different precisions in a single computation. So what's the appropriate mix of computations to, say, solve a system of equations? Rather than doing everything double or everything in single, can you combine single, double, half, quadruple in some way to get as good an answer, but in less time and with less energy? So that's one of the underlying questions here. So I'm going to talk about the, both the low and high precision ends of the picture, including telling you, just summarising what's available in hardware and mentioning a few applications. I've got a Google alert for things like half precision, so I regularly find out what people are publishing. So a lot of work in machine learning nowadays, for example, on the use of low precision. I'll refer briefly to that. So the two particular things I'll talk about towards the end are x equals b, a system of linear equations, and some recent work I've done on using iterative refinement for that, where we combine different precisions. In fact, we use 3 precisions rather than the traditional 2. And also the matrix logarithm. Been looking recently at how to compute that in arbitrary precision. And I'll talk about some of the issues that come up when you take an existing algorithm in double precision and then try and modify it to make it work at an arbitrary precision. Okay, so I'm going to start off with a few words about. But yeah, before that, just to mention that I have written an article appeared in Simon News last year, which is a sort of in words kind of overview of what I'm going to say today. So you might want to have a look at that. If you, on this slide, this B symbol, that will take you to the appropriate web page, that blog post. And there's also on my own website, there is a, where's it gone? There's a blog post on my website about the rise of mixed precision arithmetic. It's actually been one of my most viewed posts. I think it got linked to by Reddit or something. So that also, that's very short, but it also just, again, just summarises very briefly some of the things I'm going to talk about today and has some links in there. So you might want to have a look at that. Right. So I'm going to start off with a few. Some of you may already be quite familiar with this, some less so, but I thought it would just be worth going over some beginning. So a floating point number system, how do we express it and how do we do things about it? There's essentially 2 ways you can write down mathematically such a system. The one I've done on the slide is the less common one. What you probably will see if you look in the textbook is expressions like this. You write down a number as point D1, D2, up to DT, where each of these Ds is a base beta number. So you literally write down the base of the number. What we're doing here is essentially, if we multiply this by beta to the t, it's now an integer, because we're just shifting the after the dt. And then if we adjust the exponent by t, you get what is written there. So the difference between this with the expansion and what's on the slide is that on the slide you just see integers. So there's an integer m, which is the significand, sometimes called the mantissa. Beta is the base, t is the precision, and you have exponent e. So those are just 4 integers that characterize the system. In practice, the base is usually 2, although on a pocket calculator. By the way, does anybody know why the calculator? I think they still do. So your Casio calculator or Sharp calculator, whatever, uses base 10 internally, whereas all computers nowadays, of course, use base 2. So why does a calculator do things differently? Yeah, it's not so obvious. But I think the reason is that there's conversion errors between base 10 and base 2. If the calculator worked in base 2, when the user types in things like 10 times 0.1, that 0.1 is not representable exactly in binary, and you're liable to get back not 1, but there's an error in my calculator. 10 times 1 is not 1. So you avoid the conversion errors by working with base 10 internally. That, I believe, is the reason. Efficiency is not the key there. So base 2 normally, and we have an exponent range. So the exponent is not, of course, on an infinite range. It's between some e min and some e max. And in order to ensure that there's a unique representation of every number, we normally normalize things by requiring m to be at least beta to the t minus 1. So that corresponds to this representation here, that d1 is non-zero. So the leading digit in the expansion is not 0. Okay. So One of the reasons for liking this form of way of doing things is I think it makes some of the proofs a bit easier when you want to prove rounding, for example. So a choice system here is with base 2, three binary digits, and an exponent range between -1 and 3, and the non-negative numbers in the system are then by these. So F is always a finite system, and it can be a very small system, as shown here. One of the key things to note is the floating point numbers are not equally spaced. So at every power of 2, the spacing increases by a factor beta. Okay, and here's the largest number in the system, which is 7. So we're working with the real line. Now normally that subset is pretty dense. The double precision numbers, they're pretty close together. But once we start talking about half precision, things are rather different. And half precision is much more like this picture here. It's surprisingly so, actually. So that's of numbers. There's a gap here between the smallest number and 0. And so underflow is when you do a computation and you get smaller. You have to replace the answer by 0. A way of filling and getting some extra small numbers, the subnormal numbers. So remember, we said that F is normalized if there's a lower bound on this mantissa or significand M. But if we allow M to be smaller than that, we get this so-called subnormal numbers. So you have the minimum exponent E min, and you have an M that's strictly less than the beta to the t minus 1. So what's happening here is that we're getting, we're just filling in this gap between 0 and the smallest normalized number with a set of equally spaced numbers. But they have less as you go down, because we're essentially, in terms of this picture again, so this is where this, we're just gradually knocking out these D's until we have just one left. So this final number here in binary has only got really one bit of precision in it. So the good thing is it gives you some more numbers and allows a sort of more graceful way to get underflow. The bad feature is that once you're in this range, you'll lose in the numbers, and potentially that could later come back to hit you, but start to grow again and become normalized. But this is all part of, this is all featured in the IEEE standard. So the IEEE standard came out in 1985. It was the result of many years of work by a committee, of which probably the best known member is Velvel Kahan at the University of California, Berkeley. Is in the so it's pretty controversial because, as always, the committee that produced the standard, and manufacturers only wanted to have in the standard the things that their hardware supported, and so there's a lot of to and froing about in order to get agreement. If you look in the book that Paula mentioned, I do talk about the arithmetics of the days before 1980, when every manufacturer had their own version of arithmetic. And Cray computers had a not so great version of arithmetic that didn't have a guard digit, and all sorts of weird things could go wrong in the 1970s. Squared could evaluate 1, which mathematically is impossible, but there were all sorts of weird things could happen. So one of the great things about this standard was it made those weird things go away, and properties are. But from the point of view of the lectures today, we're mainly interested in the things I'm showing here. So we've got the size, the number of bits that these operands, just expressed in terms of a power of 10 as a rough estimate. And the unit round-off is 2 to the minus t. We'll see the role of that in a moment, but little u is a measure of the arithmetic, if you like. So double precision bits, there's a huge range, 10 to the plus or minus 308, and this corresponds to about 16 digits of decimal equivalent, as we all know. And if you go into MATLAB, MATLAB works in double precision, and you know that you get about 16 decimal digits worth of accuracy in a basic computation. Precision, you can see there's a much smaller range, about 8 digits worth of accuracy. So they were defined in 1985 And there's a revision of the standard in 2008, which introduced 2 new formats. So quadruple, 128 bits, about 35 digits of accuracy, and an even huger range, and half precision. Now the standard for storage, it does not actually say you need to compute with half precision, but everybody does nowadays, and it's obvious how you would. It's obvious what the standard would have said in terms of defining operations. So half precision is 16 bits, and look at the range, 5. It's really very, and it corresponds to about 4 digits of decimal digits of accuracy. So those are the IEEE defined floating point types. I was at the Higham parallel processing meeting last week in Tokyo, and at least a couple of talks, people were saying that they weren't very happy with the way that they'd split up the half into the significand and the mantissa. And they would have rather had a slightly bigger range and a bit less accuracy. But of course, that's what we have. That's what Nvidia GPU has in hardware. And so, from my point of view, I'm sticking with what's available in hardware. But there are some people thinking about different ways of breaking up those 16 bits. But of course, you do not have that in hardware currently. So the IEEE standard has all sorts of interesting things in it, like defines how rounding is done. I'll say more about that in a moment. It has nans, not a number, an inf that represents an infinity. So it actually defines a closed number system. So one becomes an inf, and an inf plus inf is another inf, and there's quite sensibly defined ways that all these things interact. But that's not really so relevant to today. So rounding, this is where you take a real number and you map it back into this floating point number system f. And essentially what we want to do is, say the number's 5.1, we want to just take the nearest number in our system. 5.9 would get mapped to 6. If we bang in the middle between 2 numbers, so 5.5, we can either map it to 5 or 6. So we need a rule for breaking. The IEEE rule is you take the number with an even last binary digit. So what I've shown you here is a theorem that says if you round x into the system f, then here's what you can say about the rounded number. So FL is the act of rounding. So round the real number x into f. And what you get is not necessarily x, but x into 1 plus delta, and delta is bounded in modulus by unit round off. Okay, so the delta is the relative error in that approximation to x. And the claim is it's bounded by little u, which in terms of the general system is a half beta to the 1 or 2 to the minus t if the base is 2. And little u is called for twice that quantity. So look at it again. Here's 1. Machine epsilon is 2u, is that distance from 1 to the next larger number. Little u is the distance between 1 and the next smaller number. And they differ by a factor beta. So a bound for the relative error in rounding x into f. Now, one thing that talked about, and I must admit I've even rarely thought about myself, but I'll put it on the next slide, is that theorem only goes in one direction. So if you round x, then the result satisfies that equality. But satisfying that equality does not imply that FLX is the rounded version of x. So this is a rather subtle point. So at the top there we've got again what the theorem said. It's called y the rounded version of x. If y satisfies the condition on the top line, that does not imply that y is the rounded version of x. And we can easily see that with an example. So here I'm taking x is 9.185. And so this line here, so there's x, which is always the same. Here's some different y. Here's the relative error between x and y, which is essentially the delta up there. So the question is this quantity bounded by little u? Well, if I take y is 9.7 and there's my x, then the relative error is bigger than. So this is clearly definitely not the rounded version of x. But each one of these, 9.6, 9.5 up to 8.8, they all satisfy the condition. suppose is the correctly rounded version of y. This is the version of y to 2 digits, 9.2. So that's the only one that is the truly rounded version. But all these other ones satisfy the condition. So what does that tell you? That if you do some analysis, theorem, and that's typically what we do, then you're not actually fully exploiting the fact that we're using rounding, true rounding. So your results are a bit weaker than they could have been. So this is why there is a whole literature by people like Jean-Michel Muller from Lyon, Siegfried Roth, who are able to prove exploit the fact that we are actually rounding. So then you can see why from that. Okay. Examples of that kind of analysis, but I just want to say it can be. So sometimes you can prove quite surprising things if you really are willing to get down to the nitty-gritty low-level details and fully exploit the nature of rounding. Actually, I'm going to come back to that one because I think I should have had that after. This is the usual model we use for rounding our analysis. And this is in agreement with what the IEEE standard specifies. So if you have two numbers in our system f, x and y, and you want to add them, let's say, the IEEE standard says when you add x and y, you have to add them exactly and then round back into the system. So the result your computer must return for x plus y is the true x plus y rounded back into the system. So times 1 plus delta with delta bounded by u. So that is certainly true for the IEEE system. And this is what we tend to use when doing any analysis of an algorithm. But as I say, that's actually slightly weaker than what we could have said if we used a more complicated model. So the IEEE standard, it's also true for square roots, which I think the standard doesn't specify. So if you want to understand point, the usual way of doing it is to start with this little model here and just sort of make use of that repeatedly. Now, there is another version of the model that sometimes is a bit more convenient. So interestingly, and this is not obvious actually, we can divide by 1 plus delta rather than multiply by 1 plus delta. So for the rounded x log y, this is just as true as the top. And the reason this can be more useful is if you multiply through by 1 plus delta, and so you basically, the delta hits this term rather than that term. And this is the thing you've actually computed. So sometimes it's more convenient to associate the error with the computed quantity that you just formed rather than the exact quantity that you haven't actually formed. It's a very subtle point, but it saves you a little, gives slightly neater back. Okay. And this is what I've just been saying though, the model is still not fully exploiting the actual nature of rounding. Go back a couple of slides, and we look at the simple computation a times b times c. Here I'm applying the model that we've just. A times b will give a relative error delta 1 that's bounded by the unit round off. Then I multiply to get another relative error, delta 2. Of course, I could have done b times c first, and then a, and if these were matrices, that would actually affect the cost, as Henry Campallo have been investigating in great detail in recent months. Doesn't really matter. So I end up with 1 plus delta 1, 1 plus delta 2, and if I drop the delta 1, delta 2, which is of second order, then I can say approximately delta 1 plus delta 2, which of course is bounded in modulus by 2u. So the precision of the arithmetic is u. Every single operation is done with accuracy u, but this particular product will have accuracy, in the worst case, about 2u. So the accuracy, the relative error of my final answer is worse than the precision, which is kind of obvious really. And in a more complicated computation, like solving a system of equations, the accuracy could be a lot worse than u. In fact, if you have an ill-conditioned matrix, the accuracy will typically depend on the condition number, and that can be big. So it's pretty normal to think that accuracy is worse than precision. But in fact, pointed out in the yellow box there, that's not necessarily true, because you can always calculate arithmetic of higher precision using arithmetic of a given precision. So there are ways of simulating quad precision, but all your variables are double precision variables. And there's many papers on this over the years. So it would actually be wrong to say that accuracy is always limited by precision, because you can simulate by essentially storing different chunks, a very high precision variable as chunks of double precision variables. So you need to be a bit careful about any statements which you might be inclined to make about the limits between precision. So this is where the Dinosaur comes in. So this is the Tyrannosaurus Stan, and he's been there for many years in the Manchester Museum. And the story is that a tourist and said to the museum attendant, "How old is Stan?" And the attendant said, "Stan is 100 million and 3 years old." And the tourist said, "Well, how can you be so sure?" The attendant said, "Well, I've been here 3 years, and he was 100 million years when I arrived." So you see there, accuracy and precision are quite different things, as that story illustrates. Now here's something that I remember putting this in the first edition of my book, and at the time it was something fairly new. I think it was available only on the Infineon processor of the late 90s. So it's the so-called fused multiply add. So we've got x plus y times z, and the idea is that you do that with just one rounding error. So normally there'd be a rounding error for y times z and a rounding error for the plus, so you'd have two 1 plus delta terms in a more complicated expression. But the idea here is to, in hardware, do the whole thing with just one rounding error at the end. And this is now supported by quite a number of different architectures. They have this so-called FMA built in. And clearly that's desirable to have such a thing, in the sense, at least in the sense of you get a more accurate result for this operation. And I think this can be done at about the same speed as doing a single multiply as well. So if, for example, you use in computing an inner, you get a result with about half the number of rounding errors. You would hope to get a more accurate result. So the revision of the standard includes an FMA now. So they specify what an FMA should do. And as I say, a lot of hardware nowadays. But there are some let's just look at these at the bottom first. So if I have a times d plus b, so semantically what does that mean? Well, if you're a compiler, you come across that expression, which do you do first? Times d first, and then use that with c and b and an FMA, so there's two ways you can evaluate that on the compiler. Which one to use? So it's not clear, it becomes ambiguous. And if you take something like this z star z with z a complex number, the answer should be real, of course. The modular. Literally evaluate this from that expression. With an FMA, xy minus yx could evaluate as non-zero. In standard floating point, x times y is definitely equal to y times x. Definition, they're both the correctly rounded version of x times y. But if you use an FMA, then you can answer. So get a non-zero imaginary part, which would be really confusing to someone who didn't know what was going on. And in a similar vein, equation, and you get the discriminant. If you evaluate this with an FMA, then you can get a negative discriminant. Mathematically, it should be non-negative. So there's a number of problems with FMAs. They can cause confusion, unexpected behaviors. But at the top there is a more positive thing. So Velvel-Kahan came up with this clever little algorithm for evaluating the determinant of a 2x2 matrix. So you see what he does is he works out b times c. Then on line 2, e is now the error times c, but computed with an FMA. And then on line 3, he adds the error back in again. Okay, so it's a bit weird, but there is a whole line of research based on this approach of representing the error in an operation and then adding it back in later. In the area of verified numerical computation, they do this quite a lot. And so that can be proved to give a highly accurate value for the determinant, as long as you use an FMA on line 2 and line 3. Okay. So FMAs are features, but also caveats.
The fact never really tell whether the compiler will use FMA or not, and especially in the presence of vectorization, that becomes almost black magic.
Yes, exactly.
So, yeah. Yes, on the math side, say whether or not this as a correspond, whether or not this corresponds to the actual computation.
Well, exactly. I guess the compiler will probably have an option where you can say don't use FMAs. Something like MATLAB running on an Intel chip. I don't think there are FMAs on regular Intel chips, as far as I know. And I don't often come across people complaining that something's gone wrong and it turned out to be because of an FMA used. So I don't know how often that happens, but it can happen. So it's just something to be aware of, perhaps. You know, check your compiler options to see if it has one to turn them on or off, and maybe try it with and without sometime and see what difference it makes. But this kind of really be confusing, couldn't it? You've got code that's literally mathematically correct, and yet it could fail with a negative square root at some point. And you might really be puzzled as to what's going on. So that was just, I thought, a few things about floating point that were worth recapping, because they're useful to know and relevant to the rest of the talk. So now I'm going to talk about low precision arithmetic. So this is, I think, a pretty hot topic. So what's available at the moment, first of all? Well, this is the ARM Neon architecture. And I know it's a bit small to read, but here it says floating point 32-bit, 16-bit, 16-bit. So two of the ARM architectures support bit arithmetic, half precision I've been referring to. And this generally is floating point, 16-bit floating point operation. So the ARM architecture has half precision. Nvidia introduced half precision on their top of the range P100 a couple of years ago. They're claiming 21 teraflops of FP16 performance. So I believe it's only on the top of the range GPU that you get half precision, but you get a lot of performance. So I think they were the first to do that. Of this, and they're quoting 24.6 teraflops of FP16 performance, and this is exactly twice the performance for single. So you're getting twice the throughput compared with single precision, and of course less power usage. So AMD also have that now. Oops, got the wrong way there. And there are others. I mean, there was a Japanese machine called it's spelled TSUBAME, Subame, built. I think it uses these Nvidias, and so they announced a certain level of FP16 performance last year. So it's because it's arithmetic. One of the main drivers is machine learning, undoubtedly. So if you Google around the term half precision or FP16 in Google Scholar, most of the hits will be machine learning papers at the moment. And the typical paper is maybe 4 to 6 pages, and it says, you know, we re-implemented part of our machine learning engine in FP16. We ran it on the standard test problems, and the performance as it was before. And yet it runs faster now, you know, less memory, less energy usage. So machine learning people seem to be finding that, and it's not only so for running the systems, you can get away with actually very even lower precision than half, maybe quarter precision, or the ultimate is just 2 bits, isn't it? Plus 1 minus 1. I've even seen claims that that is enough in some cases. So machine learning appears to be able to use very low precision. So the question is why? And I have asked a number of people, and I think there's I'm aware of three sort of general arguments. So there's a nice paper by Kathy in the Higham Activity Group on Optimization newsletter where she talks about the fact that in machine learning, from the optimization point of view, you're actually solving the wrong problem. So that she poses a problem that is the original problem that's too difficult, too nonlinear, too hard to solve. That gets replaced by a different problem. That's the one the machine learning. And since that's the wrong problem, there's no point solving it to high accuracy. That's sort of one argument I think you could take. Second argument that people often say, and it's a bit hand-waving, is that low precision provides regularization. So it's sort of adding noise into the computations. And for some reason, that's thought to be beneficial for machine learning. And the final argument is sort of my interpretation of something that was said in a different context. Jorge Nockedal gave a great talk at the Higham CSE meeting a year ago, and he talked about the fact that the stochastic gradient descent method tends to find quite flat minima and misses out very sharp, narrow minima, and that the flat minima are the better ones for machine learning. A small change along the x-axis doesn't change the value of y very much. So for machine learning, you want these flat minima. Low precision would be further encouragement to find flat minima, because in low precision you can't even resolve these very sharp minima. So I think those are possibly three components of an answer, but I've seen no real careful analysis or explanation of why low precision works in machine learning. So to me that's still a bit of a mystery. The only thing I would say is that clearly in machine learning, what's the measure of success? It's not relative error in the sense that we're used to it in numerical computation. It's more, has it recognized the difference between a cat and a dog? Has it made a recommendation in a recommendation system correctly? Whatever correctly means. So it's just a different measure of error entirely. But whatever that measure is, the claim is that low precision works fine, and hence the drive to do low precision in hardware and then to use it in machine learning. The only oh yes, I just this earlier this week. So this is a package called Deep Learning for Java, and one of my students pointed out that they have a section called about the half data type. So this is half precision, and so they're supporting this in this Deep Learning for Java package, and they're saying the reason you might use it twice less memory used, up to a factor 2 speed up in performance, but how you've got less precision than float or double, so it might become way harder, whatever that means. I'm not sure what that means, but they're giving a warning that be a bit careful if you actually use the half precision option. And they say we don't offer. Well, I'm not surprised because LEPAC don't. You would have to go in there and sort of rewrite and recompile all of LEPAC. For some routines that would be trivial, just change the data type declaration. But for others, like our algorithm for eigenvalues, you might have to worry about the convergence test. So it's not a trivial job to convert all of LEPAC to half precision. But anyway, once again, that's an example of this kind of support being provided. But here's the other application, actually earlier than machine learning. Tim Palmer is a professor of physics at Oxford who does climate modeling. And for a number of years, he's been advocating the use of low precision arithmetic. He's even written a paper called Build Imprecise Supercomputers. So he wants in hardware low precision. And his argument is, he's got this climate model with a certain resolution of the grid over the planet. And he thinks it might be better to use a finer grid, but representing the data points in half precision, than having a wider grid in single precision. And he's done lots of experiments, written actually quite a few papers now on this topic, where he demonstrates that, or gives support for that argument, that you're better off using a lower precision but having a finer grid. And in fact, one of his postdocs was at the meeting last week and gave a talk on this. So they're really very interested in the use of low precision or more generally mixed precision in their climate modeling computations. One thing that was clear from the talk last week is it's not at all a trivial job to go into a climate code and start changing the precision of some of the variables. You know, these are huge codes, and even if you can get it to work, convincing the people who do the runs to actually then use that modified code is going to be quite a big job, because these models are run for all sorts of purposes. But that's certainly an area where there's a lot of interest in the use of low precision now. Find out. Just look a bit more at half precision. Just gives again some of the key parameters. So we've got for half single, we've got the last column. Now in half precision it's only 65,504. That's the number. On that is essentially infinity as far as FP16 is concerned. The smallest normalized number shown here, so 10 to the minus 5 off. If you allow numbers to go subnormal, so here's the smallest subnormal precision you can go down. So one thing to note there is that the subnormal range in half precision is quite a large proportion of the whole range. Whereas in, say, double precision, this range here is just a tiny proportion of the whole double range. So I guess most people working in double would never know anyway, but you probably never get down here. Your numbers probably never get that small. Whereas once you're in half precision, it's much more likely you get into this range of, but it's also much more likely you'll overflow as well. Working on quite one of the big problems that you're going to have in overflow. Now that's both good and bad. That bothers me is that as we get more and more availability of FP16, people will say, oh look, I can make my code go twice as fast by running it in FP16, and they just change a few declarations at the top. They run it and they potentially get completely the wrong answer because they only started with 4 digits of accuracy. On a null condition problem, you lose those almost instantly. You'll get a bad answer, and if this is part of a huge engineering model, and you've got the bad answer right at the heart of it, you might not realize that that's being propagated to high levels and things are going wrong. So having overflow could be a good thing. It will make people realize that something has gone wrong and they'll have to then analyze what's happening. And if you want to avoid overflow, you're going to have to start thinking about scaling. So this is a bit like going back to the early days of computing when we had fixed precision arithmetic, and you had to scale all your computations and sort of keep track of the exponent yourself. And so to do a lot of work in half, you may have to do some clever scaling to make sure your number has this range. And so I think we'll see more. I think that there are things to do there in terms of scaling algorithms to fully exploit that fairly narrow range in order to get the performance that the hardware can provide. But let me give you an example of just a simple misbehave in FP16. So this is of a vector of 2 elements, and I'm taking the alpha alpha, so that it could hardly be a simpler computation. Root x1 squared plus x2 squared for that particular x. Doing it in half precision. Here's the alpha. Here's the relative error when I do that computation in FP16. And so for alpha is 10 to the minus 4. So why is that? Well, if you square 10 to you get something less than the smallest representable number. So that just becomes 0. Go to 0. And so very poor relative error. As you increase alpha, relative error gradually gets better until by this point we've now got the relative error we would expect, which is of order the unit round off little u. But once we go subnormal, that really affects. So that's just a very, very simple more complicated computations, you could get effects. And this is, as I said, much more like 16 because of the greater part of the range that's taken normal. That's the things that could go wrong. Is if we do a little bit of error analysis, if we look at the inner product of 2 n vectors, x and y. So standard bound, in fact taken directly from my book. So the for a float with precision unit round off u, the error, absolute error, is bounded by gamma n n is nu over 1 minus nu. Mod x transpose mod y. Now notice the right hand side is not the modulus of the answer. That would be mod of x transpose y. It's mod x transpose mod y. And that's potentially much bigger than the modulus of the answer. So this is not actually a relative error bound, but let's just assume it is. The constant is gamma n, which is basically n times u. So we can really look at the second order term. This, in half precision, nu is 1 for n is about 2000. So once you have vectors of length 2000, in half precision, we can't guarantee even one correct digit in the inner product. So even the sign could probably be wrong. Okay, that's a bit surprising, isn't it? How then does machine learning manage to work in half precision? They're definitely using vectors of length more than 2000. I would have thought they're therefore getting the wrong answer a lot of the time. Yet it still works. So this is something I don't fully understand. Well, that constant is pessimistic, that gamma n. In fact, if you do your summation, so that inner product is really summing n terms xi, yi. You could, pairwise, you add pairs of terms, then you add so you break the n terms into pairs, you get n over 2 pairs, you do the same again, you form a binary tree, so you add pairwise till you get the sum. There's only log 2n stages there, and you can get that n down to log 2n. So the error constant can be reduced to log 2n by that binary summation approach. So that certainly would help. But even log 2n gets pretty big fairly quickly. So that's something I'm thinking about and hoping to make some progress on, to try to understand what are. Random variables, what's the expected error or the expected error constant? That's another way of approaching things. The other thing I would say is that in the top 500 benchmark that Jack Dongar's colleagues run, people solve on the world's fastest computers. They're just about the largest. So n here, the dimension of the problem is about maybe 10 to the 8. They're asked to solve x equals b, and they have to report the residual. So they have to do a times x minus b divided by, I think, norm a times norm x plus norm b, and report that number back to Jack and his colleagues, and Jack will check if that number passes a threshold and therefore can be allowed to be entered into the list. Because the problem is, on a top-end machine, there could have been an error. A chip could have failed, a memory error. So they might have solved the problem in 5 seconds, but they might have got the wrong answer. So you need some check that the right answer has been obtained. Is how big should that residual be allowed to be before you can say it's failed? And if you just plug in the standard error analysis like I'm showing here, and you can go on from this in a product bound to get a bound for solving x equals b by Gauss elimination, you get certain constants that are very pessimistic. And apparently they get more pessimistic the larger n gets. So the residuals being reported are actually much, much less than 1 from these really large-scale solves. They're much smaller than you would expect. And that's, again, something that I don't think we fully understand. Now, certainly in those computations, they will be using the binary tree summation idea. I think that's one of the things that but yeah, for large dimensions, our existing error bounds are really pessimistic, and I think we need better ways of bounds tell us. But here in low precision, things for n is 2000. Now, just wanted to mention some nice work by Rump and Ginnerod recently. So they have shown that in the slide, that term minus nu is that if nu is 1, it's up. So this bound written at the top there is only valid for nu less than 1, as I've written. The question is, what happens if it's 1? Surely the world doesn't end, just the bound doesn't work anymore. Well, they've shown that actually you can replace that bound by nu with no second order term in both the inner product and in some other low-level kernels. And the way they prove that is by the thing I mentioned earlier. They're using more than just the model. They are fully exploiting the nature of the rounding in the addition, the subtraction, and so on. And the proofs are long and to me, I think, quite hard. So they managed to get rid of that requirement. So the analysis is non-trivial. They've only been able to analyze a few core algorithms, and if you then go beyond those and start looking at, for example, so they have an analysis for LU factorization. If you then use the LU factors to solve X equals B, though, other terms coming. So, you know, the analysis gets a bit messy again. You can't do this replacement in all algorithms. So they point out that the pairwise summation I just mentioned, which would have a gamma log 2n, you can't actually replace that by log 2nu in that case. So this doesn't always work. And the other point is, once nu is bigger than 1, the bounds are guaranteeing no accuracy anyway. You know, relative error of order 1 is not actually telling us very much. So nice as that analysis is, it doesn't particularly help in the answering the questions I've just raised about what happens for really large dimensions. But nevertheless, that's a very nice error constants. Right, well, what if you want to try out FP16 and do your own experiments? How would you do it? And I'm assuming you don't have access to one of these GPUs that supports FP16. Well, here's a couple of approaches. So simulation 1 is you convert every number from FP16 to some higher precision, single or double, carry out the operation in question in single or double, and then convert back to FP16, because we have single and double in hardware. The obvious things. So this would mean the operators. You can do this obviously in C++, Julia, MATLAB. You can just redefine every operator to mean convert, compute, convert back. Another way of doing things would be slightly different in that the higher level kernels, like matrix multiply, you could carry out the whole, so do the conversion A times B, A and B matrices in FP16, convert them both to single, say, do the computation, the whole computation in single, and then round the result back to FP16. So, but the individual operations are all being done in all the intermediate work is being done at a higher precision. Example. So the package I've used is in MATLAB. If I just type path here, see this at the bottom here, Cleve Laboratory. So this is a package that Cleve Moeller has written. It actually goes along with his textbook on MATLAB. But within that sort of toolbox is some code for overloading the arithmetic to produce FP16 operations. Say A is FP16-1, and that defined a new class. Oh, just let me start again. So he's called FP16 that he defines all the operations on that class. So if I go B is FP16 pi, and then C is B times B, and look at again, I've now got variables B and C that are again FP16. I've used an FP16 version of pi. Now you can start to do things in a double. If I go B squared, oh, that worked, okay. He hasn't overloaded every single MATLAB operation. The matrix example. If I say A is FP16 of, so I'll form a random matrix of size 3, convert it to FP16. He's not defined what inv means for variables of this class. Has overwritten the backslash, or overloaded the backslash. So that's another way of inverting, and that does work. And if I do ans times A minus I, we would expect this to be a matrix of number 10 to the minus 4, which is what we get, because that's the unit. Okay, so via this class, but unfortunately. So I certainly recommend that. for trying FP16. So here's a bit more about it. If you look at what he's in essence, it's very simple. So he's defined this new class. For example, what plus means. So if I do x plus y with x and y both f, what MATLAB will do is it will realize variables of this particular class. It will find the definition here. So it will convert x and y to double, add them, and then convert back to FP16. Multiply, same for divide. One trivial one is LU factorization. So what Cleve does is he's got a textbook version of LU, which is just the 3 nested loops written out in the obvious MATLAB way. It's not meant to be efficient. And he calls that code with the FP16 matrix A. Computes the LU and then rounds back. But I think, actually it's not so clear from this, but what happens is that A gets right, so this is the code that actually gets called. Let me just check that I've shown you correctly there. Type. Will this work? If I go at FP16/LU, does that work? Yes, that works. Okay. And let's look at LUTX. Okay, so this is just a simple implementation of Gauss elimination. But I think it's actually not clear from what happens is that this gets done in higher precision, as I thought it did. Yeah. So the point is that the rounding back to FP16 is happening at a higher level. So this is my simulation 2 of yeah, I thought it would. I must admit I'm a bit confused now because I thought it didn't, and then looking at that code it should do. So let's come back to that later, but let's assume that it didn't use the overloaded operators and just did the whole thing in higher precision. So in other words, simulation 2, which is what you would do if you were calling, say, a precompiled Blaz routine. So if you do the whole thing, if you do the whole multiply in higher precision, then round back, you will get a bound looking like this, but without the gap, because there's only one rounding to half, and that's right at the end. And similarly, if you solve a triangle and you do it in higher precision and then round the result back to half, you will not get the condition number factor that you would have got had you done the whole thing at the working precision. So in other words, you will probably answer with doing things than if you did every single operation in FP16. So if you do that, and that's what you'd be tempted to do for speed, then you need to be a bit careful about the conclusions you draw from your experiments, because you're probably getting a more accurate answer than you expected. Everything horribly slow. It's certainly, so I can't, if I solve 100 by 100 in this way in FP16, it's going to take many, many seconds. One of my postdocs has looked around at Python, Julia, other languages, and he tells me that they all really have the same problem, the overhead of overloading every single operation, converting to single or double, then rounding back, really just slows things down hugely. So simulation in software is extremely slow. So we've used this quite a bit. Cleve has written a blog post about these FP16, and he explains how it works. So it's certainly very nice, but by no means all. Now, can I type methods A? Oh, so here's a list of all the operations that you can do in FP16. These are all the ones that Cleve has overloaded. So it's a question of looking at what's not there. Clearly that's a pretty small subset of all the MATLAB commands. So you see, rand is not there. So I did rand in double, then I rounded back to FP16. So it's a fairly limited selection, but it's enough to do some. And he also has FP8. Yeah, so quarter precision, which I haven't tried at all. So there we are. Either you get access to some hard top-end GPU, or you, at the moment, can try this in software. But the software is slow. So perhaps we'll do, which is fairly short, and then we'll have a break. Rounding error analysis. So the really great name in rounding error analysis was Jim Wilkinson, who worked at the National Physical Laboratory in the 1940s. And he was a colleague of Alan Turing. In fact, Turing, when he was at MPL, did the design of the first computer at MPL, called the Pilot Ace, about 1944-45. And he wrote the design and then left MPL, went to Cambridge. So after Turing had left, Wilkinson took over the design and building of that first computer, which did its first computations in 1950, I think. It was called the Pilot Ace. And then for many years, Wilkinson, having helped build and design the computer, also used it. And Wilkinson was actually a pure mathematician by background. So he'd got this machine that he'd helped design and build that he could then use throughout the 1950s. And there were no VDUs in those days. It was all a flashing on with the machine. And so he got a huge amount of insight by running basic numerical algorithms on that very early computer. And that's what led him to become the leading expert in rounding error analysis, and to write, well, this was his first book, the original version and the republication by Dover about 20 years ago, 1963 I think it was, rounding errors in algebraic processes, the first thorough treatment of rounding error analysis. His algebraic eigenvalue problem book 5 is so Wilkinson is the hero to many people here. I'll show you. We happen to have a scan of a slide that he wrote. This is where he was explaining backward error analysis from the point he first came across it. He was looking at eigenvalue problems and also linear equations, and he was explaining how he had the idea of looking at putting the errors back on the original data in a computation, called backward error analysis. So he wrote down the equation for the residual and noticed that you could convert that back into a perturbation of, and then he imagined that the effect was the same as perturbing the original data and then carrying out the computation. Essence of the idea of backward error analysis. In 1986, and Turing Prize for his work in the. Yeah, I wanted to give a little example actually of, and summation is the topic. So the problem is to compare 1 to xn. The obvious way of doing it is with the loop I've shown you there, just summing from left to right. And the obvious analysis is to then just say, okay, let's just work through it. You know, S2 is x1 plus x2. The computed answer from our model is the true answer into 1 plus an error, delta 2, bounded by u. Then I add on x3, so the next iteration of line 3. The add with x3 will give me another error, delta 3, also bounded by u. Now plug in the formula for x2, S2 hat from there, and multiply out, and so on and so on, dot, dot, dot. That goes on, and every line the formula gets more messy, but it's not impossible to work your way through it and get a result. But what you end up with is an analysis for that particular algorithm. The more you think about it, the more you think of different ways of summing. So I could to start at the left, I could start at the right. I could group the summands in different ways. I could add all the positive numbers and all the negative numbers, then add the results. There's also the binary tree summation idea I mentioned. So there's quite a few things you could do, and at the moment, specific to that one form, way of analysing summation. Well, here's a nice thing. Think of the algorithm as follows. You start off with this set with n numbers in it. You take two numbers from the set, add them, and put the result back. You've now got a set with n minus 1 numbers, whose sum we require. And again, you draw two numbers from the set, add them, and put the result back. That until there's only one number left. And that will be the numbers. So that's a fairly general algorithm that includes a lot of interesting special cases. But the nice thing is that the analysis of that algorithm is very, very easy, as I'll show you here. So let's look at the ith execution of the loop as adding yi and zi. And here I'm going to use the modified version of the model where I divide by 1 plus delta I rather than multiply. So this is the error in that addition. It's the delta I there. Okay, that's just the standard rounding error model. Think of multiplying through now by 1 plus delta, then so I'll get a pi hat, and I'll get a delta I pi hat, and I'll get the true sum on the right. So the error in the sum is basically delta I times pi. That's the first line. Says the error in that sum is delta I times pi hat. Summation is a linear operation. Error is just the sum of the individual. So the final error is simply the sum of these delta i's times pi hat. Think about that for a moment, but it really is that simple. And I can then use the fact that the delta i's are all bounded by unit round-off in modulus to get this inequality very, very simply. So the overall error bounded by unit round-off times the sum of these pi hats. What are the pi's? They're the intermediate of the summation. So in order to minimize the error bound, we want to minimize this quantity, the sum of the partial sums. That's what that tells us. And from that, you can then go on to look carefully at summation and look at different options like, ordering from largest to smallest, smallest to largest. All the different options can then be analysed from that bound. But the actual error analysis was trivial, wasn't it? There's almost nothing to that. The interesting part then becomes straight mathematics with no rounding error analysis in it. So that's really the ideal situation. In an analysis, we keep the rounding error part very simple. Then what we need to do becomes just regular analysis. So some sort of meta comments inspired by that, and people regard rounding error analysis as difficult, I have to say. They think it's hard. So I would say it is and it isn't. So the hard thing is deciding what you want to prove. And one of the reasons that is hard is that, shown by this little table here. So in the world of matrix computations, we have component-wise analysis and norm-wise analysis. So it depends on whether you're looking at the components of the matrix or vector or just bounding the norm of the whole error. We've got forward errors. Forward error just means the final result minus the correct one. Backward error, the Wilkinson thing of throwing the error onto the data. And we've got mixed component-wise, norm-wise, where you have a combination of those two things. So when you start out analysing an algorithm, you've got to choose your components from that table as to what type of analysis you want to do and decide what you want to prove. And that's often the hardest part, deciding what you want to prove or what can be proved. We need to know what model to use. As I said, we normally use the standard model I showed you earlier, but you could do something more sophisticated. You can have a model that incorporates underflow, for example. The standard model doesn't. Or you could look more carefully at the effect of rounding. You need to worry about whether you're going to keep or discard higher order terms in the analysis. Rather than there's just a danger that you're discarding something that can be big. In fact, if you give a talk and you write down error is something plus big O U squared, you can always be sure someone will say, well, what's the constant in that big O term? I'm worried that it can get big. And so ideally you would want to track that. Do you ignore underflow and overflow? Well, usually we do, but sometimes it's more important not to do that. And again, nearly always people assume real data. So, you know, analysis of an eigenvalue solver, working with real everything, with all real data, but often we're working with complex matrices in practice. Rounding error analysis for complex data, and there are basic results that you can apply, but they're not quite as neat. That's why nobody ever does it. They just do the real case, and the complex case is pretty much the same. Maybe it's not. You know, maybe there's some subtleties you're overlooking there. So rounding error analysis. I mean, I've done quite a bit of it myself over the years. I think the hard thing is, as I say, deciding what to do, what it is you're trying to prove, what the line of attack is. If you can get that right, actually doing the analysis need not be all that hard. So I'd certainly encourage it if it's appropriate. And if you do manage to do analysis, people will probably be impressed because they think it's hard. They might not realise it's actually quite easy. So that's probably a good place to take a break before we go on to the look at higher precision. So I don't know, 20 minutes or so, what do you think?
10, 15 maybe? Maybe 10:30?
Yeah, so we'll carry on at 10:30? Yeah, okay, good. Well, let's now move on to talk about higher precision. And the first question is, why would you want to use higher precision? So I've got a collection of papers here that illustrate different answers to that. So one of the earliest papers I saw, the first one there, was talking about reproducibility. So the idea that you have you get the same answer from this if you repeat the same computation, maybe on different machines or different architectures, which is of course now is a big issue, bitwise reproducibility. And in that paper, he and Ding were talking about if you do the computations in high precision, that's one way of getting reproducibility. I mean, it's a fairly crude way of doing it, but that was something that was proposed quite early on. So I think they were using quad precision there within certain parts of some. The second example, second paper actually is a survey of applications where high precision is needed in physics. So that's worth looking at if you want to see a whole range of applications. One I came across myself was this black hole one. So they were doing simulations of black holes. They need to do long-term simulations. This involves solving a hyperbolic PDE, and they found they had to do that in quadruple precision to get the required accuracy. And they did that on a GPU in CUDA. The fourth one is in number theory. So some computations related to the Riemann hypothesis. They've got some large matrices, or dimension, I think a few hundred, and they need to compute very accurate determinants of those matrices. And they're using arbitrary precision arithmetic because these determinants are notoriously badly behaved, but they do need a certain level of accuracy in those computations. And that boils down to doing LU factorization, and then you get the determinant from the LU factors. The final one, Michael Saunders at Stanford told me about this. He was approached by some people working in biology who said, we're trying to solve some linear programs and our codes are running too slowly. Can you help us? And it turned out they were running the simplex algorithm in rational arithmetic, so exact arithmetic, because they felt they needed a good answer. So they just ran the whole thing in rational, which means that every operation, the number of digits roughly doubles. So you rapidly just fill up the whole computer memory with all your variables. So that was, from our point of view, clearly a crazy thing to do. So Michael said, no, you don't want to do that. You want to maybe just use higher precision floating point. And he worked on how to do that in quad precision. And the idea was to solve the problem once in double precision with the simplex algorithm, with Michael's code, and then use that as a warm start to another run in quadruple precision. So you've already got a good approximation. Use that as the starting guess for the quad run. And then the quad run becomes not too expensive compared with the initial run. So those details are worked out in that paper. I thought that was a nice idea. So those are just some examples of where people are proposing. But here's a completely different scenario where I think it's similar comments have been made. I just wanted to mention this because I think it's a nice analogy and example. So in editing photos, so I use Photoshop for my photos. You've got by default RGB images stored in 8 bits. And so for an m by n array, because there are three, there's r and g and b coordinates, you've got an n by 3 array. And anything you do, any of the dialog boxes, any of the tools you use, applying some function to every element of the array. So fijk of aijk. Okay, but each of those operations will incur a rounding error in general. Now, one way of looking at what's going on is if you look at the histogram. So this is the range in terms of grayscale from black to white. On the vertical axis is how many pixels have that particular grayscale value. So in this image, we've got quite a lot of very dark tones and not so many medium tones, a few really light tones. So what happens if you do a few operations in Photoshop and then look at the histogram again? Typically, it looks like this. And you see these little troughs. Well, they're caused by rounding error. Because you have to round, in practice, you have the elements are integers between 0 and 255. You have to do the operation, round back to an integer, and that causes those rounding errors. So the question is, that doesn't look very good. Should we work in 16-bit? So in Photoshop, you can convert to 16-bit from 8-bit and do everything in 16. If you do it in 16-bit, you actually do get rid of the troughs. And the difference is 16-bit 255 with a spacing of about 10 to the minus 3 rather than a spacing of 1. So from the mathematical point of view, 16 is like the way to go. You've got much better. But this has been a raging controversy for about the last 20 years if you look on the online forums about whether you need to use 16-bit. And the fact is it's very hard to find an example where it makes any difference visually. And in a sense, that's all that matters, is what we see. If you're dealing with photographs, it doesn't matter what the root mean squared error of the whatever it is might be, it's how does it look. And most of the time, 8-bit works perfectly well. And these little troughs in the histogram are irrelevant. So I think it's just worth keeping in mind that although we tend to think about normalized relative error as the right measure of error in numerical computation, depending on the application, that might not be what really matters. And so, in particular, it might not be necessary to go to high precision, even though you think it would. One or two other things to be aware of about increasing precision. So here's an example where I'm computing e to the pi of root 163 to 20 decimal digits, 25 and then 30. And the question is, what's the last digit before the decimal point? It looks like it might be 4 from that, those computations. But if I go on, you can see that in fact we just happen to have a long string of 9s. But you might have to go arbitrarily far down the precision to actually see that. So that's one issue with high precision. You can be a bit misled if you start to extrapolate from what you see with just a few precisions. And this is a well-known example. It's not one that I discovered. And another example that I have in my book, I think, is evaluating an expression. It's just x plus a sine of bx, and x, a, and b are scalars. The value is shown there. Doing this in arithmetic of increasing precisions. So base 2, the number of digits in the mantissa is increasing. The y-axis is the error. And the amazing thing here is that you get this whole range of values of t for which the error is exactly constant. And then it starts to drop again. So if you increase t by 1, 1, 1, you've done a few of these, you think, oh, I've now converged, I've got the right answer. But in fact, you haven't. You can actually get the error. So this trough could be, in principle, arbitrarily long. So if you adopt this principle of, again, you might be misled to think you've got the right answer when you haven't. So there are some strange things. So the myth is that increasing the precision increases the accuracy. Well, it doesn't necessarily do so. It will eventually, but we don't know how long eventually is in general. So the question I want to address is, if we have high precision available, quadruple or maybe arbitrary precision, how can we exploit it? How can we change our existing algorithms to make use of this high precision? well, the first question, I suppose, is the existing algorithm independent of the precision? It might be. If you're doing a Newton method, you'll have a convergence test somewhere that just says if error less than tolerance, stop. Maybe all you have to do is change the tolerance from 10 to the minus 16 to 10 to the minus 32 for quad. It could be that simple. In other cases, it will be harder. In some cases, I'll explain in a moment, the algorithm itself is already tuned to the given precision. And so if you change that precision, you have to change the algorithm in a non-trivial way. An obvious idea, and this applies to Newton iterations, is to gradually increase the precision. Since initially the error mathematically is quite large in a Newton-type iteration, you know, the error is quadratic convergence, 10 to the minus 1, 10 to the minus 2, 10 to the minus 4, and so on for Newton, ideally. There's no point computing the first iterations in 32 digits. You can do it in a lower precision and gradually increase the precision as you go along through the iteration. So that's a fairly obvious idea that could be applied. This is the point earlier. The case that in higher precision you require fewer iterations. So this is the thing that's not so obvious a point. Lower precision might give you slower convergence than you expect. So this is a benefit of higher. But what's available? So if you want to try higher precision, where can you find it? Well, the 3 M's, MATLAB, all have high precision available. For MATLAB, you would need the symbolic math toolbox from the MathWorks, or the Multiprecision toolbox from a company called Advanpix. It's a one-man band based in Tokyo. The man is actually Russian. And I'll say more about that in a moment, but that's a very interesting toolbox. In terms of languages, Julia, the newest of all these languages, has a big float data type where you can specify the precision arbitrarily. And it builds on this MPFR library. So GNOME MPFR is an open source library that builds on the MP library. This is actively under development now. One of the main developers is Paul Zimmerman in France, who I heard talk about the library last summer at the IEEE Arith conference in London. So he was saying at that conference that although MPFR is designed for high precision, you know, beyond double precision, they're actually working to optimize low precision at the moment. So they're finding a lot of people are using MPFR with double, single, or even half as the accuracy, because they want to explore the behavior of a computation in different precisions. And this is a very nice way of just tuning the precision and rerunning a computation. So they're finding people want lower precision. They're working to make this library more efficient at lower precision now. Some compilers, of course, can compile to quad precision, C and Fortran particularly. Python's got packages like MPPath and SymPy that I think support higher precision. You won't have heard of Turing. This was at the University of Toronto. So in Toronto, I'm talking to Tom Hull, Professor Tom Hull, years of numerical analysis actually. And Turing was a language developed at Toronto for teaching their computer science students to program. So it's a bit of a Pascal sort of language. And Tom Hull was developing a version called numerical Turing, which had arbitrary precision base 10 arithmetic. I think a couple of papers might have been written, but it's certainly not very well known. An attempt to support high precision floating point. So I mentioned the Advanpix toolbox a moment ago. So this is an independent toolbox not sold by the MathWorks. It's from this Advanpix company. And it provides high precision arithmetic where you can arbitrarily specify the number of decimal equivalent digits. The question this slide is about is how fast is high precision in Advanpix versus the MATLAB symbolic toolbox. So you may have heard of the VPA arithmetic in the symbolic toolbox. Similarly, that allows you to specify the number of decimal digits you want to work to. So in this experiment, I've taken 34 decimal digit equivalent, so quad precision in IEEE standard. I've done an LU factorization of a matrix of dimension 250, an eigenvalue decomposition, non-symmetric, an eigenvalue of a symmetric matrix. This is the complete eigenvalue decomposition. And I'm showing you the ratio of the time compared with double precision. So for LU, I call the built-in MATLAB LU on a double matrix. I run it once, time it, and then I call the Advampix version with the matrix now converted to 32 digits. And the ratio of times here was 98. So the quad precision computation was 98 times slower than the double one. And here are the ratios for the argument. These are the ratios for the MATLAB. And here's the ratio of VPA to MP. So what you can see is two things, I think. First of all, quad precision is maybe one to two orders of magnitude slower than double, according to this measure. And secondly, that the Advampix toolbox is actually doing quite a bit of a better job in terms of speed than the MATLAB toolbox. Now, I should say there's many different ways you could answer this question about the comparison of speed. You could just look at the elementary operations, x times y, x plus y, and so on, and just time those. But in practice, we're going to want to use library routines. And so this is arguably more meaningful to look at what is available in these packages. So in Advampix, I know the author has gone in and sort of optimized the LEPAC LU. He's converted it to high precision. He's made some optimizations. And he's got a fairly decent ratio here. So this is these are the practical ratios if you want to do a computation in MATLAB using built-in kernels. So maybe 10 to 100 times slower. And I know Advampix is optimized for that particular choice of digits of quad precision. Matrix functions, so this is something I've worked on quite a bit, as Paolo mentioned. There's quite a few algorithms for things like the exponential, the logarithm, trigonometric functions, matrix powers that use Pardee approximants. So Pardee approximants are an analog of Taylor approximants, but they're rational functions. So remember, a Taylor series is a polynomial approximation to a function about a given point, typically the origin. So e to the x can be approximated by 1 plus x squared over 2 by that quadratic polynomial. Pardee just uses a rational approximation, but with the same properties that it's good near the origin. And so we've a number of papers I've worked on have used Pardee approximations. But to determine which approximation you use, you need to know the precision that you're aiming for, because you've got the degrees of the numerator and denominator to choose. And so the algorithms that we've developed in the past have been devised for double precision. So they're aiming to get about 16 decimal digits equivalent of accuracy. So if we now change to quad precision, we need to rederive the algorithms because we're now going for a much higher accuracy. And in fact, we need to change the logic as well. So actually, there's quite a lot will change in this class of algorithms. Now, I think even in the scalar case, I think there's probably some open questions, because from what I know about the way, say, the MATLAB library, whatever it's called, does elementary functions, it's the same sort of picture. Computing the cosine, you have to do range reduction to get onto a certain interval. You then use a polynomial or rational approximation to the cosine on that smaller interval. And that approximation will be tuned for the precision. So if you now go to quad or high, and I'm not sure if that has really been looked at carefully for higher precisions yet. So going to high precision has implications for algorithm design. So I'm going to talk a bit more about that in the context of the matrix logarithm before going on finally to talk about linear systems of equations. So let's talk about the logarithm of a matrix first. But first of all, a bit of historical context here. So we're going to compute the log of a matrix to maybe 32 digits, which sounds quite exotic somehow if you've been working in double for many years. But what I want to point out is that there's nothing really clever here. People were doing this years ago. Henry Briggs in the 1600s was working out logs to 14 decimal places by hand. Logs of numbers between 1 and 20,000 and up to 100,000. And as Hermann Goldstein points out, Briggs should be thought of as one of the great figures of numerical analysis. In France, de Prony was working to 19 decimal places, and in Edinburgh, Edward Sang to 28 decimal places in the 1800s, by hand. Now, they weren't always getting the right answer, of course, but it's pretty impressive achievement.
Do you
So,
have any idea why they were doing that?
No, well, I think not really, no. Maybe by going for 28 digits, they were hoping to get 11 correct or something, I don't know. Yeah. So there's the front cover of the Briggs's book in 1624, and that's what the answers look like. Okay. So how did Briggs do it? Well, I'll explain in a moment. But first of all, again, just for a bit of context here, I'm going to talk about the log of an algorithm and a code to do that. What about log of a scalar? So back in the early 60s, when we had the first computers, had been around a few years, people started publishing mathematical software. That was new then. And the language they used was Algol 60. Fortran was around, but that Algol 60 had been chosen, particularly in Europe, as the sort of the language in which to express algorithms in academia. But Algol 60 did not have a complex data type, only had real. So Algol had a log of a real number, but it didn't even have a complex number type, let alone functions on complex numbers. So people wrote codes to do log of a complex number, where the complex number was represented as x plus iy with x and y real variables. So there was the first example. Herndon in 1961 wrote this paper, Algorithm 48. And shortly after, Relf wrote another paper. And he pointed out that Herndon used the arctan function to get the argument of the complex number. And it turned out that his code actually failed if you gave it z is naught as input. And it gave the imaginary part of the logarithm on the wrong range. So it should be between minus pi and pi for the principal log, but it was giving a different range. The other interesting thing is that that first paper used the log function spelled log, not the log function spelled ln. Now, in Algol 60, log is log to the base 10. ln is log to the base e. So that suggests to me that that code had never been run, because it would give the wrong answer for almost any input. But that's not surprising. This is 1960. You know, how would you even run a code? You'd have to hand it into the computer center, wait a week, well, debug it for about 2 weeks. It's not an easy thing to run a code in those days, so it probably hadn't ever been run. And then there's another paper by Johnson and Sangren pointing out some more problems. Division by zero was an issue with the earlier papers, and these early algorithms didn't even get the correct sign sometimes. So then Collins wrote Remark on Remarks, and it turned out that Johnson and Sangren's code gave log of 0 equals 0, which is not correct, and it had some minus signs missing in some of the statements. So finally, Collins wrote the new algorithm 243, which, as far as we know, correctly implements the log of a complex number. So it took 4 years and 5 papers to get log of a complex number. These guys are not idiots. I mean, it's just hard. It's not easy, especially without MATLAB to do things interactively when you're programming. So we mustn't forget that log of a complex number is not exactly entirely trivial, let alone log of a matrix. However, when you're doing log of a matrix, you of course build on the scalar version.
Where are these nodes and algorithms?
These are all communications of the ACM. That's where people published codes in those days. So these are all typically one-page or half-page papers. They're printed in 2 columns, and the back of the journal just had a long list of programs to do various things, of which this was one example. Yeah, so it's good to look through these old issues sometimes and see what was going on. So for the matrix case, what do I even mean by the... well, let me assume that my matrix is a square, of course, but it has no negative real eigenvalues. So I'm ruling out the negative real axis as the place where eigenvalues can lie. So a log is a matrix for which the exponential of x is a. So you give me a, I've got to find an x, so that e to the x is a. And there are many such x, but I want the one whose imaginary parts of the eigenvalues lie between minus pi and pi. That's the so-called principal logarithm. But there's infinitely many other logs, because I can just add on multiples of 2 pi I to each eigenvalue without changing the log, without changing the property of being a log. So that's what I want to compute. So let me mention one application, a bit of an unusual one. So some papers in the literature on ophthalmics talk about using this so-called transference matrix, a 5 by 5 matrix, to characterize an optical system. And in particular, the human eye is an optical system that they want to characterize. And they have a rather special structure. So the top 4 by 4 block of the matrix T, which is called S, is actually symplectic. So it satisfies S transpose JS is J, where J is this anti-diagonal matrix. So this is a very specially structured matrix. And what they want to do is take a group of observations about maybe human eyes and find an average. So what does the average eye look like? But if you average, say, 3 T's, by taking the arithmetic mean, you average 3 S's, and the result will not be symplectic. So the property of symplecticity is not preserved by the usual arithmetic mean. So what they propose in that paper is instead to take this mean. You take the T's, you average them, and then you exponentiate back. So this is mean, as it's sometimes called. And this is certainly so this mean now involves the log of the matrix and then the exponential of the matrix. Okay. You will see this expression in many different applications, people working on manifolds and things like that. Right, so how did Briggs do his computations? Well, actually, he used that line at the top there. So what he did, so he said log of x, so x is his real number that he wants to compute the log of. So he used what I've got here. So that's x to the 1 over 2 to the s to the power 2 to the s, which is 2 to the s log of x to the 1 over 2 to the s. So he knew that that was true for x. Useful? Well, if you take enough square roots of x, you get x close to 1. So he can then write that as 2 to the s log of 1 plus x to the 1 over 2 to the s minus 1. Okay, and this term is small. So he's going to choose s. He's computed these square roots by hand, of course. He's going to choose s to make this difference small. I knew that log of 1 plus y is approximately y if y is small. So this is now approximately 2 to the s times minus 1. What was the formula for? It's just taking the first order term of the Taylor expansion of log of 1 plus y, okay, to get this approximation. So he had to do some square roots and then a multiplication by a power of 2. But this last stage is fairly easy. So most of the work is in the square roots. Well, we're going to do the same sort of idea, but we're going to use not just the first order Taylor approximation, but a higher order approximation to the log here. And here is the algorithm in outline. So we want to get, he wanted to get close to 1, we want to get close to the identity. So while norm a minus I bigger than 1, take the square root of a. So keep going round and round. And once you're close to 1, or close to I, we'll use a Pardee approximant. So the Pardee approximants defined in the scalar context are approximations to log of 1 plus x, a degree k polynomial divided by a degree m polynomial. We have to choose those degrees, and then we just evaluate the Pardee approximant at a minus I and the s. Of the Briggs algorithm. Now, taking square roots of the matrix is not easy, and we can simplify things for ourselves if we first do a Schur decomposition. So line 2 now computes the so-called Schur decomposition. A is the given matrix, Q is unitary, and T is upper triangular. So this enables us to now to work with triangular matrices, because the Q's log of A is just Q log of T and Q star, so essentially the Q's just disappear from the formulae. So the square roots are now of triangular matrices, and there's a nice way of computing the square root of a triangular matrix with a finite recurrence. And then at this final stage, we're now working out the party approximant at a triangular argument, which again is easier to do, it's more efficient. So the questions are, what degree should we take for the party approximants? How should we choose k and m? And how many square roots should we take? I mean, the while loop stops as soon as the norm is less than 1, but maybe we want to make the norm quite a bit less than 1 so that we can use smaller k and m. So there's some sort of trade-off between taking more square roots but using a lower degree party approximant. So how do we choose, how do we make that trade-off? Briggs didn't try, he just wanted the first order Taylor series, so he wanted to use that Taylor series as soon as he could, but we can maybe do better by going further, and also we're working to arbitrary precision here. So I'm not going to give all the details here, I just want to give this sort of overall picture. But Kenny and Laub in the 1980s derived a very nice error bound for party approximants to the logarithm. So it's that equation at the top. So our matrix X, which has got norm less than 1, I'm assuming here, the error in the party approximant to log of I plus x is bounded by the thing on the right, and the point is that on the right we've only got the norm of x. So the right hand side is a scalar quantity. Work out the norm of x, log of 1 minus norm x, and then we've got RKM evaluated at minus norm x. The left hand side is hard to estimate, the right hand side is trivial to compute. So this gives us a computable bound for the error. And so we can think of some sort of way of using the right hand side to choose k and m so that the error is less than some tolerance. That was the idea of Kenny and Laub. So that is the forward error that we're bounding there, true minus computed. Another approach that I've used in recent years with my colleagues, Almoey, a former student, and Relton, another former student, is to look at backward errors. So we ask a different question. So we say, this party approximant, k, I know it's approximately log of I plus x, but can I write it as log of I plus x plus delta x? And how big is this backward error norm delta x? So write the party approximant as the true log of a perturbed matrix and try and bound this perturbation, bound norm delta x. The reason we prefer this to using the Kenny-Laub approach is that the Kenny-Laub bound will depend in some way on the conditioning of the problem. Whereas backward error is just entirely relative to the data. There's no condition numbers we have to worry about in this form here. We simply have to say how big is delta x compared with A. So this is a bit easier to interpret. But this requires a different analysis. We were able to do the analysis, and we developed algorithms for double precision computation. But those algorithms require symbolic and high precision work that we do offline when designing the algorithm. So we do that once and for all, then we can write down the algorithm and implement it. But this is all for double precision arithmetic. So if I now want to take that work and work out a quad precision algorithm, I have to do all that work again. And here I want an arbitrary precision algorithm. I want you to give me a precision. It might be 64 decimal digits worth. I don't want to have to run all this symbolic computation before I can run the algorithm. It's just not practical. So that approach we have to discard. And so we go to the Laub approach now for arbitrary precision. And we try and use that bound at the top once again. That bound at the top is an absolute error bound. Now, in numerical computation, we want to work with relative errors. How big is log of? Well, for small x, it's roughly norm x. Again, it's the first term of the Taylor series. So that bound at the top is actually far from being a relative error bound. And so when we first did this work, we just used the bound as stated. And we required the thing at the top to be bounded by our tolerance. And we got rather poor results. And we'd forgotten that now we work into high precision and potentially taking x very small, that this can be a small quantity. So one of the lessons from our work was we had to actually use a relative error bound instead of an absolute bound using this approximation. Because, unlike in the double precision case, the x that we end up using the one in norm. So this is a good example actually of something that things that don't happen in double precision, when you go to maybe quad precision or higher, different things happen and the algorithms need changing. So the used is to bound the forward error, use the forward error bound to minimize the number of square roots subject to the party approximant giving the required accuracy. We take k equals m, so we take numerator and denominator have the same degree, so-called diagonal party approximant. So the algorithm will choose automatically the number of square roots and the degree to give the desired error. That's the idea. And the input is the tolerance, the error tolerance. So compared with the log m in MATLAB, which uses 2012 algorithm, the new algorithm is based on forward error rather than backward error. I think I've got an error plot here. Oh no, right. So there's one more thing I want to say about that algorithm. So in this algorithm, we have to bound, in deriving the parameters, we have to bound the norm of the matrix power series. So we've got sum from I is L to infinity Ci a to the power I. The obvious way to bound that. If you have a power of a matrix, a to the k, let's say, the obvious bound is norm a all to the power k. Okay, so from your first layer algebra course, this is just the submultiplicative quantity property of norms. That's the obvious way to bound norm a to the k, and therefore the obvious thing will be to use that in the summation. The problem is this can be very weak. So for example, if I take the matrix 1, theta, 0, 1, and I'm thinking of theta as being very big, a squared is 1, 2 theta, 0, 1. So the norm of a squared is roughly for large theta, but the norm of a all squared is about theta squared. So there's a difference theta between this, and theta can be arbitrarily big. So this can be a really, really terrible bound. And notice this is what's called a non-normal matrix. It's far from being symmetric or orthogonal. It's very sort of skew in structure with that big off-diagonal entry. So in order to make our algorithm as good as possible, we came up with a way of getting a better bound for the power series than simply using this obvious inequality. This is just to give you a flavor of what we did. So the first inequality is just the triangle inequality. Then the second inequality is trivial and seems rather pointless at first. But if I define beta to be the biggest of these quantities in parentheses over all I, then I get that final bound there. So beta is the a to the I, take the norm, and then take the ith root. Now that is not a computable quantity. We can't obviously compute all infinitely many powers of a and then compute beta. But see, the point is, the idea is shown here. By using some explicit powers of a, I can maybe exploit this sort of behavior. So what we want to do is use a few low powers of a and actually compute them with the hope of getting a better overall bound. So for example, if I had to bound norm of a to the 4, I could bound that as norm of a squared all squared. So if I compute this thing, then this could be a much better bound than just norm a to the power 4. Norm a to the power 12, it could bound as a to the 4 and a to the 3. So the idea. And so what we've ended up doing is using these quantities alpha p shown here. So this is not obvious how you end up with the alpha p. But it turns out that if you compute or estimate these quantities for a few small values of p, 1, 2, 3, 4, 5 maybe, then you can get much sharper bounds for that power series than the obvious one. And all these alpha p's lie between norm of A and the spectral radius. And they, in fact, can be a lot less than the norm of A and much closer to the spectral radius. So that this leads to much better truncation error bounds for the Pardee approximation. And this is actually one of the keys to the algorithm. And I've even done some more recent work on this that has managed to improve a little bit on those constants. But the point I want to say really is to emphasize that non-normality of a matrix is often a problem in numerical computation. And this sort of behavior where the power of a norm of a power, sometimes called the hump phenomenon, exponential context, is to some extent can be dealt with by that technique. Now here's an experiment where we computed at 64 digits, decimal digits that is. So this is sort of twice quad precision. Most of these markers are variants of the algorithm I just described. So log m underscore Taylor, transformation-free Taylor, Pardee, transformation-free Pardee. Those bottom four markers are all variants of our new algorithm. What we're plotting here is on a collection of about 70 matrices indexed along the x-axis, the relative error on the y-axis. And the blue line is the machine precision, 10 to the minus 64, times the condition number of the problem. That's the condition number of the matrix log. So we want the error to be below or not far above that blue line. And the matrices are sorted by decreasing condition number. So here we have some quite nasty problems with a huge condition number. Here we've got some very well conditioned matrices. That's conditioning with respect. So we want to see whether our markers lie above or below the blue line. And for the bottom four methods, they pretty much lie below the line. These purple triangles, log m AGM, this is an algorithm in the recent paper in SciMax, SciM Journal of Matrix Analysis, that was designed for double but is easily modified. And the inverted are what was in the advanced about 2 years ago. So that's the toolbox I mentioned from Japan. So he had a log m to high precision. And what you can see is that the Advampix log m here is not doing very well. Condition problem where we're getting a fairly inaccurate answer. That's unstable. The AGM algorithm is also showing signs of instability here. I've not shown you the picture for 16 digits. Lie below the blue digits. Okay, so they all work fine in double precision, but as you increase, things going wrong. If I go to 256 digits, the Advampix green triangles have all gone off the top of the plot, so I've just tied them to the top line there. So this is completely unstable. The AGM is again showing instability for particularly. So this is whereas the new algorithm is largely doing what we would hope it would do. So I think that's a good example of going to higher precision can really test an algorithm in ways that the things that you wouldn't see happening at low precision can start to happen. So that's something we need to bear in mind. Yeah, so our new log m is written in MATLAB, and we have the course on GitHub, the code in GitHub Online. So that was just for the log. I think there's to be done on other matrix functions at arbitrary precision. It's really not just the beginning of what I think could be done here. So any comments on that or other questions?
Do you mind showing is that an exact answer, the one that lays on the bottom axis?
Actually, well, I should first of all say, how do I get the exact answer here? Well, I just evaluate to even more digits, maybe 250, 500 digits, say.
I don't remember if it was there even in the previous plot.
Same data point.
Oh, yeah.
Yeah, I wouldn't worry too much about those. what I've noticed in doing these sorts of experiments over the years is that you do sometimes get abnormally small relative errors. Now you see, think about double precision again. In some sense, the relative error should never be less than about 10 to the minus 16, because that is just rounding will give you an error of that size. But when you're dealing with vectors, you can get really small errors. And I have got a paper in ACM Toms with my former postdoc Nick Dingle, published about 4 years ago, where we explored that phenomenon. Why is it that the relative error in a vector can be much less than the machine precision? And it's to do with having a vector with elements of wild scaling from large to small. And what we noticed was when we're doing these sorts of pictures, the errors can be, I'm profiles here, but if we were to plot performance profiles, these abnormally small numbers can really skew those profiles. And so what we proposed in that paper was a way of sort of lifting up these really low numbers to make the so in this case, I can't remember whether we've just artificially brought that number up from somewhere way down here, or it just happened to be there. I forget now. But to me, the fact that these numbers are way below the blue line doesn't really matter. All I want to know is that they are, not way above it. Being really small is just a fact of having badly scaled vectors or matrices. Okay. Shall we carry on, or do you want to take another break? What do you think?
Yeah, I think I would
Just carry on? Okay. So the final section is on iterative refinement. So this is, I think, really practical stuff, because this is x equals arguably the most important linear algebra kernel after matrix multiply. So non-singular n by na, I want to solve x equals b. I'm thinking about LE factorization. So a could be sparse, but I'm assuming I can still factorize it. And the question is, can we do better by exploiting different precisions? So can I beat the LA pack in some way by exploiting hardware precision or software high precision? And the approach I'm going to look at is refinement, which is a very old idea. In fact, it goes back to the 1940s. Wilkinson actually programmed this on that very first computer at NPL in 1948. And I've got a tech report where he explains what he did. So the idea is you solve the system, your working precision here is double, that's the base precision, and he computes a solution via LU factorization, a couple of triangular solves there. He then forms the residual, R b minus ax x naught, in quad precision. Now on early computers, often you could get this residual in high precision at no extra cost, because when they did a multiplication, they actually formed it to high precision and then rounded it back to double. So all you had to do was grab that result before it was rounded back. So his R was essentially no extra cost. He then solved for this correction vector d in double precision, and then he added d back into the original solution x naught. Now if there were no rounding errors, then x1 would be exactly equal to x. And you can think of this as Newton's method if you like. But Newton for a linear problem is not very interesting. In practice, there are rounding errors. x1 is not the true solution, but you can go around again and now do the R for x1. And so that's what Wilkinson did. You iterate round until convergence. And this became a very popular method. It's in early textbooks. But from the 1970s onwards, computers were no longer able to provide the residual at no extra cost. And indeed, it might not have been easy to even do R in extra precision at all, because your compiler might not have provided quad precision. So this usage started to die out a little bit. And so in the 70s and 80s, people thought about, well, what if you do the whole thing at the working precision? Is there any benefit? Because originally people thought, well, there's no point. What's the reason? Well, Skeel and Jankowski and Wozniakowski showed there is a reason for doing this. There's two things. One, you can prove that you get slightly better error bounds than for the original x naught. So the bound for the converged iterate will have a somewhat smaller error bound, a smaller forward error bound than the one for x naught. That's the first thing. And that wasn't easy to prove. That was quite complicated. The second thing is if your original LU is rather unstable, if it's got some error growth, if you've used a rather weak pivoting strategy, this process can cure that instability. So you can get by with a more lax pivoting strategy. Again, both these papers prove that. So that fixed precision usage became popular in the 70s and 80s. In the 2000s, there was a machine called the IBM Cell Processor came out, which I think was used in some of the early gaming systems. Jack Dungara and his colleagues got hold of one of these early chips, and they found that single precision ran about, I don't know, 10 times as fast as double, or maybe even more. There's a huge difference between single and double. And they thought, can we exploit this? And they came up with this version of refinement. So here the base precision is double, but they factorize A in single. Now that's going to be very fast. They do the residual solve in single, update in double. So it's a mix of single and double designed to exploit the speed of single precision. And they gave some analysis that showed this, and experiments that showed this could be about at least twice as, could be twice as fast as the doing the whole thing in double. So what I'm going to talk about is a refinement process where we allow 3 different precisions. So little u is the precision that you give A and B in, and that I'll return x in. That's little u. U sub f is the factorization precision, which could be less than u. It could be a larger precision, so less accurate. And UR is the precision at which I compute the residuals. So 3 different precisions satisfying that inequality. So all the previous examples are special cases of this. And the question is, can we somehow choose these 3 precisions to get a faster and maybe more accurate algorithm? So I'm thinking of the precisions I choose from as being half, single, double, and quad. Well, I'm going to need some error analysis for this. So what's available? Well, Wilkinson's book that I showed you earlier for fixed point arithmetic, as that was what was popular then. Moeller gave the first analysis for floating point. That's Cleve Moeller, the inventor of MATLAB. In the first edition of my book, decided I would try and do a general analysis that covered all previous cases. And I published that. Unfortunately, my analysis doesn't cover the form of refinement that Dungara et al. Used, but they had their own error analysis. So all the above analyses are for at most 2 precisions, and they also require that the condition number of A, remember kappa A is norm A times norm A inverse, it's a measure of the difficulty of the problem, that times the precision is less than 1. So what we've done in this work, and this work is joint with Aaron Carson, who's at New York University, that applies first to any solver, doesn't have to be just LU. It looks at backward errors and forward errors. I'll focus mainly on the forward error here. And it will allow the condition number times u to be bigger than 1. More about that in a moment. So this covers in particular the Dungara et al. Approach. And there are some assumptions for the analysis. So remember, AD is R is the residual, D is the update. I'm assuming that when I solve that system, I get a relative error less than 1. And I'm calling it UF times theta. So it will be some multiple of the precision of the factorization. I'm calling that multiple theta I. So that's a pretty weak assumption. I'm just saying we get a bit of accuracy in the update. I'm also defining a quantity mu, which is a bit mysterious at first sight. Where that mu comes from. So you probably remember that the norm of a matrix is normally defined as follows. Okay, so given some vector norm, we define the norm of the matrix as the maximum stretch ratio over all vectors. That's the subordinate norm, as it's often called. So by definition, the norm of a matrix times a vector is bounded by the norm of the matrix times the norm of the vector. So if I take any particular x in this expression, then clearly this must be true. So that's straightforward. So when we're doing analyses in numerical algebra, we use this inequality all the time, without even thinking about it. We use it many, many times. So let me replace x by x minus xi hat. So xi hat is the computed iterate from iterative refinement. Is an obvious inequality that you would just use without thinking. And I in particular have done that inequality many times in the past. But the point about this work is that we realize that this can be a very weak inequality. So I'm going to write down, rather than just bound it by the product of the norms, I'm going to say let's call that mu times that product, and recognize that mu is at most 1, and in fact mu can be very small. If you work it out and it's not hard, mu is possibly as small as 1 over the condition number. So this can be a really weak inequality, really weak. And so that's almost the key thing in what I'm going to tell you. It's one of the 2 key things, just recognizing how weak that inequality can be. Everyone before us has always just written that down without any comment. But we're going to and see if we can say something about the behavior of mu. What does a cow say in German? It says moo in English. Does it still work? I'll need some condition numbers. I mentioned kappa a moment ago. We've got Skeel in the 1970s introduced these con condition numbers. So that the absolute value of a matrix means take the absolute value of each element of the matrix to get a new matrix. And so we have these cons, and they are no bigger than kappa, but all these condition numbers are at least 1. The cons have some nice scaling. You multiply by a diagonal matrix on the left, then that diagonal matrix disappears in this expression. It just factors out. So I'll need some kappa. So here's a version of the 3 precision iterative refinement. And it says if this quantity in the first yellow box is less than 1 throughout the iteration, then the error goes down, the forward error goes down until it eventually converges to something satisfying this bound here. So here's the Skeel condition number, you see. I've also got a kappa up there at the top. So that in the standard analysis, you would have mu I equal to 1, which would mean you always get the kappa appearing, the full effect of the kappa in the phi there. And in the standard analysis, you would have, for this UF theta, again, you would have a kappa dependence. So what you can maybe get a hint of here is that in this analysis, we maybe are able to cope with large condition numbers because they're going to get multiplied by numbers possibly less than 1. You can also see here that if I have a lower precision for the residual, then that can counteract any ill conditioning in the final error. So if this, for example, is the square of our working precision, then in most cases this will just be of order u, and I'll get a perfect relative error. We also have a backward error result which is a bit less interesting, it's more standard, but this basically says that you'll get as long as the problem is not too ill conditioned, you will get a small backward error, which is what we already know really. So what are the cases of interest? Well, let's denote S, D and Q are 4 different precisions. And in this table, I'm going to show you the precision for the factorization UF, the working precision U, and the factorization and the residual precision UR. So what Wilkinson did in 1948 would have been DDQ. He did residuals at quad precision, everything else at double. So this first column is sort of traditional usages. The red just means I'm bringing in the availability of half and quad, and the half is certainly a recent phenomenon. So in the 70s and 80s, people did everything at the same precision. In the 2000s, this is the Dongara version, where he did the factorization in single, but worked at the base precision double, residuals in double. And if you want to use 3 different precisions, then these are the 4 interesting cases that we could look at. So there's quite a lot of different possibilities there. And I'm particularly interested in these. So this table just summarizes the results I've shown you in I think, a fairly informative way. Again, we've got the 3 precisions. we've got a bound on the condition number such that the remaining columns hold true. So what do these columns mean? If you look at the first row there, where I've written an S, that means we get an error of order 10 to the minus 8, the round off for single precision. So the backward error, either normwise or component-wise, is of order 10 to the minus 8. The forward error is bounded by cond AX times 10 to the minus 8. So each line is in general different. The yellow lines are the 3 precision variants. Let's focus in on 2 particular lines, the yellow and the pink. So the yellow line says that if I factorize in half precision, but my base precision is single, so why is this interesting? Well, if I factorize in half precision, most of the work is in the factorization. That's where all the n cubed work is. So I would hope to double my, or halve my computation time by factorizing in half and doing a bit of refinement for just a couple of steps maybe. So double precision residuals, but I need the condition number to be bounded by 10 to the 4. If it is, I get essentially perfect backward and forward errors. This pink line is for the more standard refinement with just 2 precisions. Here I can allow the condition numbers of 10 to the 8 in order to make the same conclusions about accuracy. So here I'm factorizing in single though. So this will probably be twice slower than the yellow line, but it gives me a larger range of problems that I can solve. So the message from that slide is, if you want to factorize in half precision, hopefully fast, but I can only solve a smaller range of problems. I can't allow the condition number to be bigger than, which is a bit of a restriction for single precision. You'd really like to allow condition numbers up to 10 to the 8. So is there any way we can get the speed benefits of the HSD line while allowing a larger range of condition numbers? Well, let's go back to the analysis. Is shown in yellow, and for that to hold, we need both those terms in the yellow box to be less than 1. The second term is the error in the update, the error in that solve, and the first term involves this mu defined like that. So I would like to argue that the UF theta can be less than 1, and I'd also like to be able to argue that this mu term is small, because mu will hit the kappa and hopefully counteract kappa. So, well, it turns out that mu I is normally less than 1, much less than 1, and it converges to 1 as the iteration converges. Why? And how can we exploit that? Well, here's an observation that I found in an unpublished technical report from 1990 by Siegfried Rump. So he says, if you take a matrix A and you factorize it LU, and you then multiply the inverses of the factors back into A, then you will get a condition number of that new matrix, which is roughly 1 plus kappa AU. So the original got condition number kappa, which let's say is 10 to the 16 for a nearly singular matrix in double. But just this preconditioning will reduce the condition number by a factor U. And this even works when the matrix is numerically singular. Let me just demonstrate that in MATLAB, because that is quite a surprising claim. So I think I tried this earlier. If I can just okay, pause. Oh, I'll just type it again. So a good way of getting in condition matrices in MATLAB is by gallery rand SVD. Rand SVD. Let's take a 5 by 5 matrix with condition number 10 to the 12. Do LU and look at the condition number of L inverse A, whoops, times A times U inverse. Okay, so the A's got condition number, well, let's print it out, 10 to the 12 in the 2 norm, and LU should be lowercase. let's dot print L new to make it fit on better. Okay, so my initial matrix has got condition. After this scaling, it's got condition number 1. Is that what Rump said? Yeah, because he said the condition number gets multiplied by the unit round off. The unit round off is 10 to the minus 16, so that will certainly get rid of the 10 to the 11. What if I make this 10 to the 16 now? Yeah. A numerically singular matrix, again, condition number gets down to order 1 after you do this preconditioning. Make the condition number bigger than 10 to the 16. Make it 10 to the 20. Well, the problem is, with round SVD, you cannot get condition numbers much bigger than 10 to the 16 because of the rounding errors in the formation. But I can do something different. I can use the inverse Hilbert matrix built into MATLAB. Inv Hilb, this is the exact matrix, the exact inverse of the Hilbert matrix. So 13, let's try inverse Hilb 17, say. Okay, so here, the condition number of 10 to the 21, Rump says that will get reduced by a factor 10 to the minus 16, and it does. Okay, so Rump was right. Remarkable. So this is even despite the fact that L hat and U hat are inaccurate LU factors. Well, their inverses are inaccurate because they're still conditioned. So what we're going to do is exploit that observation.
Provided that you do at least the partial pivot.
Yes, so this is LU with partial pivoting, yeah. So what we're going to do is take the update equation, AD is R, and precondition it with these factors. We're going to apply both inverses on the left, in fact. So I multiply by U inverse L inverse. My equation ADI is R now becomes A tilde DI is this preconditioned right-hand side. So now to solve that system, we're going to use GMRes. So we of course don't want to invert any matrices, but we can apply A tilde to a vector. To apply A tilde to a vector, you have to do a multiplication with A and 2 triangular solves. We will do those in extra precision. And the key point is that the condition number of A tilde is much less than that of A from the Rump observation. The error analysis shows that we will get an accurate DI, and so the condition that we get some accuracy in the update will be satisfied. And we'll call the overall algorithm GMRes IR. But there's one caveat here. Not in the past really to res. When I came to do this work with Aaron, the main thing I realized was there being hundreds of papers on the convergence of GMRes. Since GMRes was invented in about 1982, we still don't really understand what makes it converge fast or when it converges fast. And it is not directly related to the matrix, interestingly. So you might think having a well-conditioned matrix would mean GMRes would be fast to converge, but that's not the case, at least if A is non-normal. So there's still a question about how quickly GMRes will converge here. Another point I wanted to make, there is some work before ours by a couple of Japanese authors using the same sort of idea, but they were explicitly forming this matrix. You know, they were explicitly inverting U and L, explicitly multiplying into A. So that gives a very different type of algorithm that wouldn't even be applicable to sparse matrices. So here's what the analysis shows when we use this GMRes idea. So with LU, the first 2 lines are what I showed you earlier. The GMRes approach has the benefit that it allows a much larger range of condition numbers. So we can now, if we use this half, the idea of factorizing in half, so here the working precision is double, factorizing in half, I can allow condition numbers up to 10 to the 12 now and still get perfect backward and forward errors. So GMRes does a very good job of handling the ill conditioning of the matrix through this preconditioning operation. So if you compare the first line in pink with the first line in yellow, the only difference is the much, much larger range of condition numbers that we can accommodate. Now the convergence I've shown you that says when refinement converges is very reliable in terms of predicting what happens. The only uncertainty in everything is how many iterations GMRes will take. So at each outer iteration I have to solve this preconditioned update equation. How many GMRes iterations are required for that? That's the question. If it requires a lot of GMRes iterations, the whole thing will be too expensive. Let's try some 100 by 100 matrices. So these are random matrices, actually from gallery rand SVD. So they've got exponentially distributed values, and the condition number here is 10 to the 10. The working precision is double. We're factorizing in single, and we're looking at the forward and backward errors. NBE is normalized backward error. CBE is component-wise backward error. And we can see that this is just not converging. The refinement here is not converging after 2 steps. Would it help if I compute residuals in quad precision? No, makes no difference whatsoever. In fact, the theory says that, because the theory, the precision for the refinement does not appear in the convergence condition for the iteration. So that's not surprising. The difference here is I've got a better condition matrix, 3 different precisions, and I'm getting convergence into iterations. So this is all just with standard LU. This is not the GMRes version so far. So that's a nice case where you can factorize in much lower precision. Let's turn to the GMRes examples. So this is a case where we're using double precision as the working precision. The matrix is actually pretty ill conditioned for double precision, 10 to the 10. We're factorizing in single, and we get convergence after 2 iterations. Perfect forward and backward errors. How many iterations does GMRes require? Well, 2 on the first step, 3 on the second step. So GMRes converge very quickly in this example. So this is a case where we're definitely getting a big benefit over, say, standard LEPAC, because most of our work is in that single precision factorization here. Here what's the difference? I'm now using half precision for the factorization. I've got a pretty well-conditioned matrix. The refinement converges quickly, and GMRes converges quickly. 8 iterations in each case. So this is an example where we can get away with using half precision. So remember, we're factorizing in half, even though the working precision is double. So that's potentially gets factor 4 speed up over a double factorization. Here's, again, half precision factorization, but a fairly ill-conditioned matrix. Refinement still converges. Now, interestingly, the x0 gave an overflow. So the initial LU factors computed in half, I guess, must have had maybe there was a 0 on the diagonal of u, but I got overflow. So what do? Well, we just set x0 is 0. So interestingly, the refinement process is powerful enough to work even if you give x is 0 as the starting vector. Now, what's funny about that is that this is starting to, if you do that, you're starting to change the refinement into almost like a separate algorithm. You're just not using the initial LU factorization solution at all, and you can almost think of moving towards a kind of GMRes algorithm. So that works quickly, but unfortunately, GMRes takes 100 iterations, and n is 100 here. So this is a case where the refinement still works fine, but the cost of solving the update equation is just too high. So this is essentially a failure for this approach. Okay. So because we don't really understand convergence of GMRes, we can't really predict in advance when that will happen versus that will happen. So the speed of convergence of GMRes is key, but it's very hard to know in advance what's going to happen. There's lots of questions I've not addressed here, like what are the GMRes convergence tolerances we use? There's many different variants of GMRes that we've just used the sort of plain variant here. There's variants that reuse previous matrix vector products. There's flexible GMRes. So there's a whole lot of things you could do to take this work further. But at this point, the results are, I think, very promising. And Jack Dungar and his colleagues have recently published a paper where they tried these ideas out on a GPU. And I think they're reporting speedups of 1.8 over the sort of standard LEPAC style double precision algorithm. So I guess they're comparing LEPAC in single versus factorizing in half, as I've described it. So most of the work is hoped to be at half precision. They get a 1.8 speedup. So not quite the factor 2 we might hope, but reasonably close. Okay. So that actually takes me to the just about the end, and there's a few overall comments here. So we've talked about both low and high precision becoming more available. Low precision in hardware, high precision in software. I think there's a lot of work to do on low precision, on understanding what we can compute, how we can avoid overflow, how to exploit the full range and accuracy of half precision. This refinement example is a case of where just using a little bit of high precision is helpful. So the amount of high precision is only really order n squared in the algorithm I've just been describing. So that's small compared with order n cubed. So more generally, you know, can you take an algorithm, just do a little bit of high precision somewhere, and make the algorithm perform better? Now there has been some work on that for the, did you do that? Yeah, I thought, yeah, you've done that for the eigenvalue problem. Okay, so ask Paolo about how that works for the eigenvalue problem. That was a paper in maybe CISC a few years ago.
Yep.
Yeah. And then we had the idea of using 3 precisions in refinement. Hopefully benefiting from the fast early factorization, using GMRes on the preconditioned system. And the thing I didn't emphasize too much was we are able to handle here matrices that are singular to working precision and still actually solve X equals B accurately. So that's a bit surprising. For matrix functions, we saw that the whole rederiving and reworking, the logic can change, the parameters of the approximations can change. So there's going to be a lot of work to do there if we try and take other algorithms into the high precision context. I think I've got some references at the end of the talk here. The papers with Aaron Carson, one appeared early this year and the other's about to appear. And the paper with Max Fassi on the log, I just sent in the final galley corrections early this week, so that will appear fairly soon as well. Okay, so that's about it, but there may be some questions perhaps.
Thank you.